So as you know, our goal is to aggregate gradients in the context of federated learning using additive secret sharing technique, specifically the additive secret sharing technique that we learned in the last several sections. However, the secret sharing technique that we used was only working with integers, but federated learning gradients tend to be decimal numbers, right? So we want to be able to convert our decimal numbers into an integer format so that we can actually aggregate them using a secret sharing technique. And for that, we're going to look at what's called a fixed precision encoding. And it's really quite a simple technique. And we're going to go through a little bit of it here. We're not going to dive too deep into the theory and unpack it, because this is really the kind of thing that you want to lean on a toolkit. So you're going to lean on PySift to really do this for you. But it's important to know sort of how the information is being encoded under the hood, mostly so that if you get sort of undefined behavior, maybe you set the precision too low, or you want to tweak performance in one way or another, you can just have a general idea of what this fixed precision encoding is really about, just so you can be knowledgeable of what's going on under the hood. So the first thing we want to do is we want to choose what precision we actually want to represent, which means, you know, how many decimal points we actually want to encode our numbers with, right? So if we're going to take a decimal point like 0.5 and we're going to encode it as an integer, we have to know how much storage we actually want to set aside for information that's after the decimal point. So for that, we need to set our base, which we're going to use base 10 encoding, which means that we're going to use normal encoding if you wanted to think about it that way. We could also use base 2 encoding, which would be binary. And we're going to set a precision to be 4. So in this case, this is saying that we're going to encode numbers with base 10, and then we're going to have 4 decimal places that we're going to allow for storage. And then we also want to have a Q value, and we're going to use the same Q value we were using in the additive secret sharing technique. And this is going to allow us to handle negative numbers, as we'll see in a moment. The first thing we want to do is we want to create an encode function. And this is going to take our decimal number and convert it into an integer. So we're going to return, and it does this using a really simple technique. It literally just takes our input decimal and multiplies it times base to the power of precision. In this case, it just multiplies it by the number 10,000, converts it to an integer, and then takes the modulus, so mod q. So if we want to encode the number 0.5, we can now encode it as the number 5,000, right? So 5,000 actually means 0.5. And we'll actually see that there are other kinds of ways that we do arithmetic that allow us to actually do decimal point operations while everything is being stored in this integer type state. Cool. So let's do a decode function. So decode is literally just taking the same process in reverse. I mean, it's quite simple. So we'll say x fixed precision and return x if x is less than equal to q divided by 2, else x minus q. And here's the main part, base to the power of precision, right? So previously, the main part is we multiplied it by fixed precision. Now we're going to divide it by the size of our precision. And this is really just making it so that we can take into account sort of negative numbers. So if we encode a 0.5 as 5,000, we can decode 5,000 as 0.5. And so if I did negative, so this ends up being a really large number. It basically wraps around the other side of q, and we can decode this as negative 0.5. So here we go. This is how our fixed precision encoding works. A good example of addition, if I were to sort of add two numbers together, so add 0.5 with 0.5, so we say 5,000 plus 5,000, so decode 5,000 plus 5,000 decodes to 1. So some of these fall out naively. Multiplication, other operations can be a bit more tricky, but again, it's not something I want you to worry about too much, because you're really going to lean on top of a toolkit to handle sort of fixed precision encoding for you, in the same way that you lean on your processor right now to do most of the low-level arithmetic for you. It's just good to have an idea for that this is happening under the hood to enable you to be able to use these secret sharing techniques, that you're actually converting all your numbers into these fixed precision format. And in this particular case, if the precision is set at something like 4, it also means you're losing a few decimal places worth of value, right? So if originally we're using a 32-bit encoding and with this big decimal value, which is our gradient, we're going to lose the end of that if we're using a precision that only allocates 4 decimal places of precision. And we can make this larger or smaller. It'll affect performance and memory and things like that. That's just a good thing to sort of understand and take into account when you're adjusting your fixed precision encoding. All right, and with that, let's move on to the next section.